Following on from the previous session where we had a review of relative extrema, this section is going to require us to use that understanding and combine it with the recent knowledge that we've acquired about trigonometric functions. So there are two questions here to have a go at, which are fairly tricky. So perhaps try and have a go at them, and then if you need to, have a look at the following explanations to get you started. Question 1 then gives us the function fx equals sin x plus cos x. We're given the domain here between 0 and 2 pi. Importantly, you'll notice here it says analyze it without using a GDC. So we're supposed to be doing all of this without a calculator. First of all, we're asked to find the x and y intercepts. Well, one way we can do that initially is to look at what happens when our y value is 0. So sin x plus cos x equals 0. So therefore sin x equals negative cos x. So thinking back to the unit circle, the only place where the sin x and cos x have equal absolute value but different signs are going to be in the second and the fourth quadrant. So we know that they will have the same value at 45 degrees or pi by 4, but the sign is the same. So it'll actually end up in the second quadrant being 3 pi by 4, or in the fourth quadrant 7 pi by 4. So that's going to be the y-intercept, and we can therefore find the x-intercept by setting f of x equal to 0. We know that sine 0 plus cos 0 will give us 1 because cos 0 is 1. So that will give us the y-intercept. For part B, it says find the intervals on which f is increasing and decreasing and the relative extreme points. So from the previous video then, this requires us to differentiate the function. If we differentiate, we end up with cos x minus sin x. We then need to set it equal to 0. So cos x minus sin x equals 0. Cos x equals sin x, and we've already mentioned that this is the case at pi by 4, and here we are looking at the domain between 0 and 2 pi. So this is the first and the third quadrant here. So at these 2 points, we know that the gradient equals 0. Just like we did previously, we need to substitute in some points in each of these regions here, and if we do that, we can ascertain that the first derivative is positive between 0 and pi by 4, in which case it is increasing, and it is also increasing between 5 pi by 4 and 2 pi, and in this region here it is decreasing. So we have established where it is increasing and decreasing, and we're also asked to find the relative extremes. So because it is the first derivative is changing from a positive to a negative here, in this instance we are looking at a relative maximum point because the gradient is increasing up until here and then decreasing, and similarly at this point it's decreasing, the gradient is decreasing and then it's increasing, so it must have reached a minimum. So we need to find the y coordinate by taking pi by 4 and substituting it back into our original equation. And similarly, to find the coordinates of the relative minimum, we're going to take 5 pi by 4, substitute it back into our original equation, and we should end up with these coordinates. For part C, it says find the intervals on which f is concave up and concave down, and also find the inflection point. So here, this is the second derivative. So the second derivative is negative sin x minus cos x. Again, we set that equal to 0 to find possible inflection points because we can solve for x. So here we're looking at the values of which negative sin x equals cos x. So in this instance, we would be looking at 3 pi by 4 and 7 pi by 4. So here we're looking at the second quadrant where we've got negative x coordinates. So if we take the negative of the positive y coordinates, those would also be the same. And we can also see that in the fourth quadrant we would have positive x coordinates, and we would have negative y coordinates. So if we take the negative of a y coordinate, that would also give us a positive, so they would still have the same value. So again, on our sketch, we're going to put these points here and test to see what happens either side of them. So again, substitute some values either side in here, and we can elicit that where the second derivative is negative between 0 and 3 pi by 4, it is concave down, as it is between 7 pi by 4 and 2 pi, and it is concave up between 3 pi by 4 and 7 pi by 4. We know, because the gradient here is 0 and the sign changes, that these are both inflection points. So in order to establish the inflection points, we need to substitute in for these two values into our original function, and if we do that, we will find that the y coordinate in both instances is 0. Using information from parts A to C, sketch the graph of f. So we've already established the coordinates of the maxima and minimum, and we also established the inflection points are here. So we can establish also finding the two extreme points, so finding the output when our input is 0 and 2 pi, this will be the shape that our function takes. As you can see, quite a long and protracted question. For the second question then here, show how to use the second derivative test to find the x-coordinates of the relative extrema for the function ln x, or ln x plus sine x, on the domain x between 0 and 2 pi. And then secondly, find the global extrema of the function fx equals x plus sine x squared on the closed interval 0, x between 0 and pi. In the first one then, so we're going to have to start by finding the second derivative. So we've got our function here, ln x plus sine x, and we can therefore just, because we're adding, just differentiate each of these and add them together. If we set that equal to 0, we can solve that on a GDC. So this will be from a GDC question. Set that equal to 0, and we can graph that and find that we would actually have solutions at x is approximately 2.04 and 4.48. So these would be where the stationary points are. The second derivative then, as we said, we need to find in the question here, we're being told that. So this is our first derivative. If we differentiate that, we will end up with this. Again, we can just differentiate these each individually and add them, or as it turns out here, subtract them. The second derivative at each of these points can be calculated. So if we find the second derivative of 2.04, we can find it's negative. Therefore, we've got a relative maximum at this point. And similarly, we can find the second derivative of 4.48, and because it's positive, we have a relative minimum at this point. So again, this is another way of testing maximum and minimum using the second derivative test. So negative values will elicit a maximum, and positive values will elicit a minimum. In part A for this question, we're asked to use the second derivative test to find the x-coordinates of the relative extrema. So in order to do this, we've got our first derivative, f dash x, equal to 1 over x plus cos x, and then we can set that equal to 0 in order to find the x-coordinates of the relative extrema. So the easiest way to solve this is graphically. So if we plug it into the graphical calculator, we can see that there will be two solutions. So we'll have a value of x equals 2.07 and at 4.49. So once we've got those values, we can then establish the relative extrema by substituting into the second derivative. So first of all, we need to find the second derivative. So if we take the derivative of this, we end up with negative 1 over x squared minus sine 2x. If we substitute in for 2.04, we end up with negative 1.11, and as this is less than 0, it means we have a relative maximum at the point x equals 2.07. And similarly, if we substitute in 4.48 and find the second derivative, that yields a value that's greater than 0, which means it must be a relative minimum at x equals 4.49. For part B, find the global extrema of the function f of x equals x plus sine x squared on the closed interval x is greater than or equal to 0 and less than or equal to pi. So in order to do this, first of all, we need to find any stationary points. So the first derivative is 1 plus 2x cos x squared, so we're going to have to use the chain rule to differentiate this. And once we've got that, we can set it equal to 0 and then use a GDC to solve that. So we'll find that there will be 3 stationary points at 1.392, 2.115, 2.834. We can then find the output or the y-coordinate of those values by substituting in these values into our original function here, which will yield these 3 respective values. However, because we're asked to find the global extrema, we not only need to consider the relative maxima and minima, but also the largest and smallest value within the range. So if we take the smallest value, which is f of 0, we get a value of 0, and the largest value, pi, if we take f of pi, we get 2.71. So the global extrema is not just looking at the relative maximum minima, but all of the points within the region. So we've tested the smallest and the largest as well, and from that we can see that the maximum, the global maximum, the largest point will be here at 3.82, and the global minimum will actually be f of 0, which is the smallest value in this entire interval.